Hey there, folks, me again. All right, this is going to be 3.5 Vsepr. That's how you kind of say that little acronym there. And that stands for Valence Shell Electron Pair Repulsion. So that's what we're going to talk about in this particular video. We're going to start out by talking just simply about the shapes of molecules. Yes, molecules actually have shapes and why that's important. The shape of a molecule actually will affect that particular molecule's reactivity and its behavior. So the way that this thing is organized, the way that it is structured will actually determine how it's going to react with other things, how it's going to freeze, how it's going to melt, and it's going to give us some really good indications about the particular reactivity of that molecule. And the shape depends on a couple of factors. These include really three things. Atoms forming the bonds, so what atoms are involved, the distance of those bonds, and then finally the angles of those bonds. So all three of those things affect the shape of the molecule. Vsepr is kind of going to focus mainly on that third point there, the bond angles. That's the important one. So we've got to go over a couple of definitions, couple terms before we move on. In a molecule, some of the valence electrons are shared between atoms to form covalent bonds. And we've been doing this with our Lewis structures. And we call these things bonded electrons. So the red arrow is kind of misleadingly pointing to the bonded electrons here. It should probably be pointing more towards like these guys. Those are our bonded electrons, right? They're there, right there. Okay, bonded electrons. All right. The other electrons that could be in our molecule are not bonded, and sometimes we call these non-bonding electrons, or probably more often, and what I use are lone pair electrons. So that's these guys up here. So if you drew the Lewis structure for oxygen, or for water rather, because this is water, that Lewis structure, which I think you already have in your books, would look something like this. You'd have oxygen, and then hydrogen, and then hydrogen, and then you would have lone pair electrons. See, those are the lone pair. Right, that's probably how we drew it in our book. But guess what, folks? This is not the appropriate shape for a water molecule. It actually looks a little bit different, and we'll discuss why in a second. It's all about Vsepr. All right, so Vsepr. Here's the idea. In all covalent molecules, electrons are going to try to stay as far away from each other as possible. As far away as possible. They do not like being close to each other. And this is just common knowledge because they're all negatively charged, and negatively charged things will repel one another. So both bonding and non-bonding electrons repel. So what we're looking at with this image at the right side of the page is the electrons that are here, those are bonding electrons, want to be as far away from these electrons, and they want to be as far away from these electrons, and they want to be as far away from these electrons as electronically possible. Okay? So the shape of the molecule, therefore, depends on a couple of things. Depends on the number of regions of electron density, okay, we'll get to that in a second, that it has on its central atom, and whether these are bonding or non-bonding electrons. So what do we mean by electron density? That's just the region or the area where the electrons are. So for instance, this particular molecule has what? 4 regions of electron density. See that? 4 separate regions. And how many are bonding? Well, 2 are bonding. We have 2 bonding regions, 2. And how many are non-bonding? Oh, we have 2 non-bonding regions as well. So those are the things. Electron density, how many of those do we have? And then how many are bonding and how many are non-bonding? Those are the things that are important. Once the dot structure has been established, so once you've drawn the Lewis dot structure for that particular molecule, the shape of the molecule will follow one of the basic shapes depending on, again, the regions of electron density around the central atom, and the number of regions of electron density that are occupied by bonding electrons. So here are your basic shapes, and in fact you do not have to write this table down because I do have it in your chemistry manual. I have a bigger one for you. The most common shapes of molecules are here to the right, so some molecules are linear, they look like straight lines, and some are bent. Some are tetrahedral, which is kind of a neat name. Tetra, that's 4. Tetrahedral is like a 4-dimensional object. Trigonal planar, oh my goodness. Trigonal, well, you might hear like triangle there, and planar means it's all in a plane, so a triangle in a plane. And then there's some other weird ones there. So if you go to page 123 in the chemistry manual, you should kind of know the first 5 that are in that manual. And out of those first 5, I know linear is one of them. I think angular or bent is one. I think tetrahedral is one, and trigonal planar is one. I think the only other one is trigonal pyramidal. So this dude and this dude, you do not have to know those two. So you want to kind of know those first 5. You want to know what the shapes are. Linear, I mean, come on, we're going to bent. That's pretty simple. And the other 3 you're just going to have to kind of memorize. All right, so let's take a look a little bit closer at each one of these. A linear molecule. Linear molecules have only 2 regions of electron density. And so we can actually use a little abbreviation for linear molecules. It's AX2, and I'll show you what that abbreviation means in a second. So carbon dioxide, CO2, this is a linear molecule. It only has 2 regions of electron density. Okay? What the A means in this little symbol, the A always means the central atom. Okay? The central atom. The X refers to the number of bonding electrons. Okay? Bonding pair of electrons. So we have, there's 1 bonding pair of electrons. There's 2 bonding pair of electrons. So we call AX2. So that symbol is, or it denotes a linear molecule, AX2. Okay? So only 2 regions of electron density. And so remember what Vsepr does is the electrons want to get as far away from each other as possible. We'll have an activity in class to show this. They want to get as far away from each other as possible. So if this electron density for some odd reason was like up here, well, that wouldn't be good because now this angle is only, what, 90 degrees. And they're not as far away from each other as possible. So instead, the angles go opposite of one another. So now that angle is what, like 180 degrees. And then that's as far apart as they can be. So that's linear. The second one, angular or bent molecules have at least 3 regions of electron density, but only 2 are occupied. So I'm going to give 2 different examples here. We're going to give the SO2 example and the H12 example. So these are examples of bent or angular. We're going to lump those 2 into the same group. And we're going to start with water, the one on the bottom. Okay, if you notice the little symbol down here, the little code, again, A represents the middle atom, which is oxygen. Okay, X2. Remember the X is how many bonding pairs do we have? Oh, we got 1 there, and we got 1 there, so X2. And then, if you drew the Lewis structure for water, one thing you would notice, okay, one thing you notice is that there are electrons, lone pair electrons on that central atom. And they want to get, again, as far away from the other bonding pairs as possible. So they're actually going to force the water molecule to bend. If you look at the water molecule, it's actually bent. And that's so that all of the electrons, bonding and non-bonding, can get as far away from each other as possible. That's the idea behind Vsepr. Okay? So this code that I have over here, AX2E2, is actually specific for the water molecule. The sulfur dioxide molecule, right, it would have a different code. Its code would be AX2E, right? Because it only has one pair of non-bonding electrons right there. So A again is the middle, so that'd be sulfur in this case. X2, X1 and X2, so there's 2 bonding sites. And then finally, the E is this guy right here, is the lone pair electron. You can see the lone pair electron right there. There it is, where oxygen has 2 lone pair electrons. All right, moving on. Trigonal planar. Trigonal planar, all occupied by other atoms. So in this case, our code is AX3. Carbon dioxide is a great example of this. Every single region around the central atom is occupied by shared electrons. And that's the look of a trigonal planar molecule. Or sometimes, like in this case, a trigonal planar ion, right? Because this wouldn't be a molecule. Why is it not a molecule? Because of the 2 negative charge. That's an ion. And finally, trigonal pyramidal. Okay, trigonal pyramidal, the code is AX3E. So we have 3 regions that are occupied by other atoms and 1 by lone pair electrons. Okay, so if we take a look at the molecule itself, it actually has kind of a pyramidal shape, right? Looks like a pyramid. That's where the pyramidal phrase comes from. You guys can kind of see that pyramid right here. Okay, there's your pyramidal shape. But it really only has 3 regions where there are actually elements. So 1, 2, 3. So if you just look at the molecule itself, it only looks like a triangle shape. The electrons up here give it the pyramid effect. And those electrons up on top are the ones that pull or push the hydrogen atoms down. Okay, they push the hydrogen atoms down. So this is trigonal pyramidal. So again, the nitrogen in the middle is the A. Okay, the X3, 1, 2, 3. And then finally that E right there is represented by the E there. So you know AX3E means you got 3 bonding electrons, 1 non-bonding pair. All right, I do have one more. Tetrahedral is my last one. So tetrahedral molecules have 4 regions of electron density around them, and they're all occupied by other atoms. And this is the great example, methane, which is the gas that comes out of the Bunsen burners before you light them. And this is carbon. Carbon has 4 hydrogens around the outside, so the code is AX4. And as you'll notice, again, what's happening, we want the atoms to be as far away from each other as possible. So if you, and we'll draw these in class, we'll actually build them with molecular model kits. You will notice that this hydrogen is actually coming out of the page at you. Okay, it's coming towards you. Whereas these hydrogens, I'm going to do those in a different color. Let's do them in yellow. These hydrogens right here are actually going back into the page. So you're going to notice when we build these things, we're going to use gumdrops to do that, that the shape that they take actually does amplify or make the angles between the atoms as great as possible. Okay, that's Vsepr.